today we will discuss the basic concepts of power electronics converters. So let's say you want to design a really simple DC-DC converter which you have input of 100 volts and you want to supply 50 volts to a 5 ohm resistive load. So how can you design a converter like that? Maybe the simplest solution is just use a resistive divider, and you can adjust the resistance here, and you can, if you adjust it to 5 ohms, basically you will have 50 volts and 50 volts divided here. But of course, if you are supplying 500 watts, the power loss in this converter would be 500 volts as well. So basically, this is not a really efficient device, and you can have a most efficiency of 50%. And you can do the same thing with a linear regulator, like a BJT based regulator. So you can have a reference voltage from here, and you can adjust the gate current of that transistor. So basically it will be no different from the resistive division. So you will have 50 volts drop on that transistor. So basically again the efficiency of this converter will be 50%. So this is basically the linear regulators like LM7805 converters work like that, and they are not efficient at all. So what we can do is you can use an ideal two switch position. So in this case, if it is at position 1, basically you can just directly conduct 100 volts here, and if it's at point 2, basically the output voltage will be 0 volts. So basically if you can adjust that duty cycle, which is VG is 100 volts here, or you can give 0 volts here. So in order to get 50 volts here, so you can basically give 50% on time and 50% off time. So basically it will be not a perfect DC output, but it will be more or less like a square output. So what you can do is you can include maybe some filter elements here in between. Let's talk about an LC filter as a low pass filter. So basically that low pass filter helps us to regulate the output voltage. Again, it will not be an ideal DC output, but it will be much better than a square wave. But more importantly here, if that switch is ideal and there's no resistive components in those inductor and capacitor, so basically you will have negligible loss here. So that kind of converter can supply 500 watts. Again, the power that you are drawing from the input will be around 500 volts. So the efficiency will be much higher compared to a resistive division and also a linear regulator. So basically this is a more realistic example. So in order as that switch, I replace that ideal switch with a MOSFET, so and a diode here. So whenever you send an on signal here, basically it just conducts. So MOSFETs work as a on-off switch, and we have the diode here just as a connection from the ground. We will talk about that connection in the following weeks. And we have the LC filter here, and of course you need to adjust the duty cycle, and I need to have a feedback system, and I have a sensor, a voltage sensor, and I am comparing it to my reference input. If it is lower than that, I am increasing my duty cycle. If it is higher than that, I am reducing my duty cycle. So basically this is a controller that tries to keep the output voltage constant. So this is a more realistic power converter application. So again, let's have a look at that example. Here we have the ideal switches, and I have the load here, and I have a DC voltage in this case, and my load, I want to give AC voltage to that load. So basically if my switch on that side and that side are at position 1, basically I am applying a positive voltage. If they are at position 2, I am applying a negative voltage. So by changing the duty cycle, so here you have a large negative voltage and a smaller positive cycle, and then they are going up, and on the other hand you have here a high portion of positive voltage and a low voltage of negative voltage. So actually if you filter that thing either with a capacitor or with an inductor, so if you just think about the fundamental component of that waveform, you can achieve a sinusoidal output which we will talk in the following weeks. Okay, and common points so in power electronic devices we avoid using lossy elements. By lossy elements I mean using any kind of resistors or linear mode BJT transistors. They are all causing some power losses, so we don't want to use that kind of elements. On the other hand, we want to use capacitors and magnetics, inductors or transformers, and of course those transformers have some resistive components, but they are not directly resistive loads. And we use switch mode devices like MOSFET, IGBTs, that kind of transistors, which are not operating in the linear region, but they are working as a basically electronic switch which can be turned on or turned off. And you will see that thing in this course quite a lot. So basically you have an ideal switch and it just cuts off the current, or it can get into the conduction range. So which factors make a switch ideal? So let's discuss about those things. So basically ideal switch has no voltage drop in the on state, so it is like a perfect conductor. And this zero switching time, when you say okay turn off, it just immediately turns off and there will be no switching time at all. And when it is at the off stage, there is no leakage current as in a transistor, so it is like a perfect insulator, so there is no current leakage. And then of course there should be able to carry infinite amount of current, and it has capability of blocking infinite voltage. So in a normal transistor, both that voltage and current are limited. So what happens if you turn off an inductive load? Actually I give this example in electromechanical energy conversion, or basically if you have an inductor load, you have L di over dt, and if you just quickly turn off an inductive load, L di dt gets into infinite voltages, so it will cause some sparks and that kind of things in the switches. And the same thing happens with a capacitive load. So basically if you have a capacitive load and if you just turn on a capacitive load, or if you just short circuit a capacitor, it will cause infinite amount of current to flow, which we don't want. So of course in a practical switch, so we have the conduction losses. So if you use a normal, again it can be a mechanical switch or a MOSFET kind of switch, so you always have some conduction losses. There are some voltage drop and there are some leakage current. And also the switching time from on state to off state, or from off state to on state, it doesn't happen instantaneously, so it will require some time, and that is one of the main practical issues in power electronic applications. And then we will have, during the switching losses, during the switching we will have switching losses in the system. So basically it will cause your system to generate some heat. And of course any kind of MOSFET devices or transistors have limited current and voltage capacity, so if you get over of the defined current limit, you can damage the device. Or even if it is at the off stage, if the voltage that is blocking gets over its maximum voltage limit, you can still destroy that device in the off state. And apart from that, even if you are not exceeding voltage capacity or current capacity, you can still damage the devices, because those devices have limited dV by dt and di over dt rating. So you shouldn't pass those limits which are specified in the data sheets. Okay, so let's have a look at some general rules in power electronics. So we don't want to short circuit voltage sources. Okay, if you have a voltage source, you don't want to get a short circuit between its terminals unless the voltage is zero. And the same thing happens for current sources. We don't want to open or turn off current sources. So basically if you just turn off a current source, you have L di over dt, which goes to infinite, and you will have high voltage induced. So basically just to in the same relation, so inductors behaves like current sources, and basically capacitors behave like voltage sources. So basically you don't want to open circuit an inductor while it is carrying a current, or you don't want to short circuit a capacitor while there is a voltage stored in it. Okay, so let's have a look at inductors in steady state operation. So if an inductor is at steady state, so it is also called inductor volt-second balance. So average value of an inductor is 0 in the steady state. So we will discuss that thing in the recitation time in the next hour. So basically the positive and negative areas of inductor voltage cancel each other. So let's say you have inductor here, which the output voltage can be written as L di over dt, right? Or I can write the inductor current as 1 over L integral of voltage over dt, plus of course the integral term comes with 0. So if this is a cyclic current, so if this is, let's say, from 0 to, I don't know, some period, so that means if that integral term is larger than 0, that means that the inductor current is keep increasing and increasing. So in other words, if you apply a positive voltage over an inductor over time, that will keep increasing the current. So if the inductor current is under steady state, so that means that one is the inductor current. So basically it just, sits in a region. But however, if you just apply a non-zero voltage, so basically the inductor current will keep increasing. So because of that property, basically if the inductor is under steady state condition, so that means basically IL0 is equal to IL at after some period. So if this is the case, that is only possible if the voltage area is equal to 0. So in other words, the positive and negative areas of a inductor voltage will be equal to each other. We will see some examples in that in the following weeks. Okay, so you have the same thing with the capacitor. So basically the capacitor voltage is, you can write capacitor current is equal to C dVc over dt, and you can write the same thing, the capacitor voltage is equal to 1 over C integral of IC over some time. So basically if you just pump, if IC is always positive, so that means you are charging and charging and charging, so basically that capacitor voltage keep increasing. So in order to have a steady state or a more or less constant within some boundaries voltage, so that means the amount of total charge and discharge, or the integral of the current over some period, should be 0. We will see those things in the following weeks. So basically for inductor, so the positive and negative areas of the inductor voltage is equal to 0, or in a capacitor, positive and negative areas of capacitor current should cancel each other. So let's look at some performance parameters for waveforms. So how do you decide an output is better than another? So let's say you have two waveforms, so one of them can be 5, you have a DC component of 5 volts, and on top of that you have a sinusoidal component 0.5 sin x, and the second one is, you have again the same amount of this is 0.25 sin x, but again you have a high frequency component, this is 10 times x. So basically it looks like much ripple, but actually the total amount of ripples is the same with the previous one. So how can you decide this waveform or the previous one are better, or which one is more sinusoidal? So for example, if you have that waveform, so basically it is a sine component plus 0.3, the third harmonic component is just a plus, so basically it just distorts the sinusoid like that. And in the next one, the only thing changing is instead of a positive value, I have a negative value here. So with that negative value, or our sinusoid is distorted like that. So which one is more sinusoid? So basically we need some parameters to evaluate that kind of waveforms numerically. So the first one, which you already familiar with, is the RMS, the root mean square of a waveform. So basically RMS is the, if you have a current, or it can be any signal, you take the square, okay, then you take the mean, okay, then you take the root. So root mean square. So RMS is quite commonly used in AC systems, and we will discuss the importance of that in the following weeks. So basically the physical meaning, what is the physical meaning of an RMS? If you think about it, it is actually the average power dissipated if that voltage or whatever current is connected to a 1 ohm resistance. If, for example, if this is a current flowing through 1 ohm resistance, the power, instantaneous power, is I square R, which is 1, and you integrate that power over the period, so it gives you energy, and then you basically take the average of that thing. And again, RMS is not only calculated with pure sinusoids. Voltage or current can have many harmonics. So if you have a voltage waveform with the first component, second component, third component, etc. So if you want to calculate the root mean square of everything, apart from numerically, basically it is equal to the square of the RMS of the first component, square of the second component, square of the third component, and you add all those components and you take the square root afterwards. So this is the total RMS of a signal. Okay. Another important factor is the distortion factor. So distortion factor is the ratio of fundamental RMS to the total RMS. So if you have a sinusoid with different components, so basically it is the ratio of the fundamental component I1 RMS divided by the total RMS value. So basically you can probably answer that question, what is the dF of a square wave? How can you calculate the distortion factor of a square wave? So basically I will let it for you to calculate, but of course if you remember from the previous years, if you have a square waveform and the fundamental component will be 4 over pi for the first harmonic, if this is 1, the sinusoidal component will be 4 over pi here, and then you will have the first component 4 over pi magnitude, and the third component will be 4 over pi multiplied by 1 over 3, fifth component, and it is 4 over pi 1 over 5. So it only have the odd harmonics, and it goes like that. So it will be basically, if you can remember, the 1 is the first harmonic, 1 over 3 magnitude of the third harmonic, 1 over 5th, 1 over 7, and it goes like that. So basically, I am leaving it to calculate that value. So what is the displacement power factor? So displacement power factor is the power factor that you have seen so far. So basically you can have a waveform, let's say this is some voltage waveform, and let me use a different color. So let's say you have a current waveform like that. Okay, so if this is the current, so basically the difference between these two, okay, so this is the phase difference, so basically cos phi of those things will give you the power factor. Okay, but this is what we call in this course as the displacement power factor. Okay, displacement power factor is due to the phase differences between the fundamental components of these two signals. When we say basically true power factor, what we mean is the ratio, okay, ratio of the real power to the total apparent power, including all the components. Okay, so when we say power factor in this course, we mean the true power factor, but if you are looking at the fundamental components, you need to understand displacement power factor. Okay, so let me show you an example for the perfect sine wave. Of course, for the perfect sine wave, both displacement power factor is 1 and also real power factor is 1, so displacement power factor is equal to power factor. But for distorted waves, basically the power factor, okay, power factor should be less than displacement power factor. So let me give you an example. So for example, here you see a grid voltage, but the current is not perfectly sinusoid, but like that. But as you can see, basically the voltage is current is more or less symmetrical. So if I just take the fundamental component of the current, okay, it will be like that. So this is the fundamental component of the current. So basically, since they are symmetrical, there is no displacement power factor phase difference. So basically, displacement power factor is 1 for this signal. But of course, if I draw the third harmonic, fifth harmonic for that signal, it will be different. So basically, that is the main reason in this case. I mean, you can see from the waveform as well, true factor is less than 1 in this case. Okay. Another important parameter is the THD, which is so short for total harmonic distortion. We will hear this term quite a lot in this course, so please be familiar with this one. So it is the ratio of the RMS of the harmonics, excluding the fundamental, to the RMS of the fundamental components. So you take all the harmonics except the fundamental, and it is the ratio of the fundamental components. So basically it can be written as in two forms, either like that, so basically you just add all the harmonics, but you are starting from the second one, so the fundamental is omitted, and you are all calculating that the total RMS is due to that one, and then you divide it to the fundamental RMS component. Okay. In other words, it is the ratio of power in harmonics to the power in the fundamental components. So that is why, from the power point of view, why it is important for in this course and in many applications. So it is quite important for power quality, and you can see it like many limitations in different standards. And it used to be less than 5%. So if you are designing any commercial device, basically in order to connect it to the grid, the THD level should be less than 5%, but like in 6 years ago, it was increased to 6%. You can click on the links, and the main reason is nowadays we are using like many computer power supplies, phone chargers, that kind of things, UPS systems. They are basically injecting, because of their nature, they are injecting quite a lot of THD to the system, and the standard was relaxed a little bit for that transition. Okay, so again, THD can be written as the ratio of the total harmonics, or what you can do is you can get the total, you can get the total RMS of that signal. So that is the the equivalent RMS of that waveform, and you subtract the fundamental, basically, which is equal to that component, and then you can again divide it with the I1 RMS, and I1 RMS, it will give you the same waveform. So in some cases, for example, I asked it in the previous slides, so what is the RMS of a square waveform? Of course, you can calculate it from the harmonics, but you don't have to do that. Basically, what is it? The RMS is equal to, remember, the square of that waveform. Okay, and you integrate it, and you just take the average, and you just take the square. So basically, what will happen if this is like 1 and if this is minus 1? Okay, if you just take the square, if this is let me write here I over t, so basically if you just take the square of that waveform, so it will be a constant DC, right? If you just take the constant DC, then you can take it the average, and basically you can take the square root. So basically the RMS, the total RMS of that signal would be equal to 1. Okay, so basically then you can calculate the fundamental harmonics. So basically the fundamental harmonic is a sinusoid with the fundamental component I1 is a sinusoid with 4 over pi magnitude. So basically you can calculate that one, and basically that is our second question in a minute. So before that, let me talk about the distortion factor. Distortion factor can be also represented. I will derive that thing in one question in the following weeks. It is 1 over 1 plus THD squared. Okay, so I want you to answer this question as well. Derive, please, just don't Google it from the internet, because it is important to have some similarity with that kind of operation. So please try to derive the THD of a square waveform yourselves. Okay, thank you.